Hey everyone, in this video we're going to go over section 3.3, derivatives of trigonometric functions. And I want to first off say that all of our trigonometric functions are going to be functions of theta measured in radians. I guess it could be functions of x, but when we say sine of x, or if we say cosine of theta, these are always going to be measured in radians. Okay, so first off, if we just graph y is equal to the sine of x, it's going to look something like this. It's going to start in the origin, go up and down and up. And it would continue in that direction as well. So this is y is equal to the sine of x. And now the derivative of y prime, is going to be the slope, or the y value of y prime, I'll say that. The output of y prime is the slope of this tangent line. So right here, the tangent line has a slope of about 1. So the derivative would have a height of about 1. At this point, sine has a horizontal tangent line, so the y value would be equal to 0. And at this point on sine has a slope of about -1, would be down here. Similarly, a horizontal tangent line, and we'd be right back here, and slope of about 1. And we got one more back here for good measure. So if we were to connect these dots, we get something that looks like this. Something that goes through the point 0, 1 instead of 0, 0. And in fact, if you look, this looks a lot like the graph of y is equal to the cosine of x. And it actually is. We'll go through and we'll derive that. We'll show you that the derivative of the sine of x is equal to the cosine of x. But first, we're going to need one thing. Then we're going to use it to prove another thing, and both of those things we're going to use to prove the thing that we want. First off, remember that the limit as theta goes to 0 of the sine of theta divided by theta is equal to 1. So I should have wrote that on the back. We will use that right here. So first off, the limit as theta goes to 0 of the sine of theta divided by theta is equal to 1. We're going to use that, and we're going to prove something. We're going to figure out what the limit as theta goes to 0 of the cosine of theta minus 1 divided by theta is. So if we immediately try and plug this value of theta in, we'd get 0 divided by 1 minus 1 for 0, so we've got to come up with other means. What we can do is we can multiply top and bottom by a cosine of a theta plus 1 divided by a cosine of a theta plus 1, and that'll give us the limit as theta goes to 0 of cosine squared of theta minus 1, all divided by theta times the cosine of a theta plus 1. And so if you don't remember, sine squared of theta plus a cosine squared of a theta is equal to 1. One of the most important things you'll learn in a trig class. And what this says, if we rearrange this equation, cosine squared of a theta minus 1 is equal to a negative sine of theta, negative sine squared of theta. So we're going to perform this substitution right here. This is equal to the limit as theta goes to 0 of negative sine squared of theta, all divided by theta times the cosine of theta plus 1. Close that parenthesis. Perfect. So let's take a look at what we have here. We can regroup our numerator. After all, this is sine of theta times a minus 1. For convenience sake, I'm just going to pull this minus sign up and out, and I'm going to group one of these sines with one of these thetas, and I'm going to group another one of these sines with this cosine of theta plus 1. This will be equal to negative 1 times the limit as theta goes off to 0 of the sine of theta divided by theta times the sine of theta all over the cosine of theta plus 1. Now we know what the sine of theta divided by theta is as theta goes to 0. That's equal to 1. So this will be equal to 1. And if we look, the cosine of 0 is a positive 1, so we can plug 0 into this factor. We won't violate the domain. This will turn into negative 1 times 1 times the sine of 0. I'm sorry, the sine of 0 is 0 all over 1 plus 1. Negative 1 times 0 gives us 0. So what we have shown is that the limit as theta goes off to 0 of the cosine of theta minus 1 all over theta is equal to 0. We're going to use this result and this to prove that the derivative of sine is cosine. And let me get a new piece of paper. So let's begin. I'm going to write those two results that we need. We're going to use the fact that the limit as theta goes to 0 of the cosine of theta minus 1 divided by theta is equal to 0. We're going to use the fact that the limit as theta goes to 0 of the sine of theta divided by theta is equal to 1. And we're also going to use the fact that the sine of a plus b is equal to the sine of a times the cosine of b plus the sine of b times the cosine of a. From this we actually can get our double angle identity, our sum to product formula. So let's begin. So by definition, the derivative, so we can say the derivative with regards to theta of the sine of theta is equal to the limit as h goes to 0 of the sine of theta plus h minus the sine of theta all over h. So we're going to use our sum to product formula. Call this the limit as h goes off to 0 of, we would get the sine of theta times the cosine of h plus the sine of h times the cosine of theta minus the sine of theta. All of that is going to be over h. Now what we want to do is we are going to regroup. We are going to group these two together. Let's write this out. We'll take the limit as h goes off to 0 of the sine of theta times the cosine of h minus the sine of theta all divided by h. And then what's left over, we're going to have plus, and I'm going to distribute this limit. Now we'll do one thing at once, plus the sine of a h times a cosine of a theta all over an h. And now what we want to do is we want to factor out the sine of theta from over here. And I'm going to pull it out front. And same thing with the cosine. So this is going to be equal to, yeah, we'll do that. We'll call this the limit as h goes off to 0 of, we'll do that, the sine of theta times cosine of h minus 1 over h, plus distributing this limit across addition, the limit as h goes to 0 of the cosine of theta times the sine of h all over h. And if we look, the limit as h goes to 0 of the sine of theta, well, that's just sine of theta. That's effectively a constant as far as this limit is concerned. So we get the sine of theta times the limit as h goes to 0 of cosine of h minus 1 over h. Well, that's going to be equal to 0. Then this plus sign is going to drop down. And then we get, well, the cosine of theta is effectively a constant as far as this limit is concerned, so we can pull it out front. The cosine of theta times, and the limit as h goes to 0, sine of h divided by h is equal to 1. That will cancel, and what we have shown is that the derivative with regards to theta of the sine of theta is equal to the cosine of theta. And looking at my notes, I believe the book did this entire derivation with the sine of x. Whatever we call the variable, the result's going to be the same. d theta of sine of theta is cosine of theta. d dx of the sine of x is equal to the cosine of x. So, now that we have this, the derivative with regards to theta of sine of theta is equal to cosine, let's do example 1. And it says, so if y is equal to x squared sine of x, what's y prime? Well, the thing to notice is we have the product. We have the product of x squared and the sine of x. We have to find a derivative, so we should use our product rule. What our product rule says is that y prime is equal to the derivative of our first times our second plus our first times the derivative of our second. And that's it. You could clean it up a little bit. Say y prime is equal to 2x sine of x plus x squared cosine of x. And if you really wanted to, you could factor an x out. I would stop right there if I were you guys. Another example. Let's talk about what the, well, we'll say this. I found a typo. So by the same sort of work, if we wanted to take the derivative of sine, of cosine, you would have a cosine here and a cosine here. You would split it up here. You would regroup them, and you would use the same limits. We would actually find out that the derivative with regards of theta of the cosine of theta is equal to a negative sine of theta. A negative sine of theta. We get a minus sign when we take the derivative of a cosine. But knowing that the derivative of cosine of theta is equal to negative sine of theta, and the derivative with regards to theta of the sine of theta is equal to the cosine of theta, well, every other trig function is built up of these two. So, if we wanted to take the derivative with regards to theta of the tangent of theta, well, tangent is the same as the sine of theta divided by the cosine of theta. And now we're trying to take the derivative of the quotient of two things. We've got a rule for that. We'll use the quotient rule. The quotient rule says the derivative of sine divided by cosine is low, d high, minus high, d low, all over low, low. Now we have to go through and evaluate these derivatives. Cosine of theta, the derivative of sine is a cosine. And the derivative of cosine is a negative sine. And if you look, now this minus sign and that minus sign we can group together, turn this into a plus sign. What we have is, and I'll just rewrite, we have the cosine squared of a theta plus the sine squared of a theta, all divided by a cosine squared of a theta. Well, sine squared plus cosine squared is equal to 1, so this is equal to 1 over the cosine squared of theta, and 1 over the cosine squared of theta is the same as the secant squared of theta. Almost ran out of space, but our next derivative is that the derivative with regards to theta of the tangent of theta is equal to the secant squared of theta. We've got d theta sine theta equal cosine theta. We've got d theta cosine theta equal negative sine theta. We could, by the same approach, d theta of the cotangent of theta, well, that is actually equal to a negative cosecant squared of theta. We can have a d theta of a secant of theta, and that's going to be a secant of theta times a tangent of theta. And finally, d theta of a cosecant of a theta is equal to a negative cosecant cotangent. So take a look at what we have. So sine went to a positive cosine. And then we had a secant went to a positive secant tangent. And we had a tangent go to a secant. But we had a cosine go to a negative sine. We had a cotangent go to a negative cosecant squared of theta. And we had a cosecant go to a negative cosecant cotangent of a theta and a theta. The cos, when you take their derivative, go negative. Cosine goes to negative sine, cotangent goes to negative cosecant, and cosecant goes to negative cosecant cotangent. Secant goes to sectan, sine goes to cosine, tangent goes to secant. But if you're taking the derivative of a trigonometric function that starts with co, you need a minus sign. So, at this point, this seems like 6 new derivatives you have to have memorized. I personally only have 2 of these memorized. I know that sine goes to cosine and cosine goes to negative sine. When I need the derivative of tangent, I derive the derivative of tangent. When I need the derivative of cotangent, I derive what I need. That's equal to low. D high, the derivative of cosine of theta is a negative sine of theta, minus high. D low, derivative of sine is a cosine of theta, all over the denominator squared. Well, we get a negative sine squared minus cosine squared. I can factor out a minus 1 and call that negative 1 times sine squared of theta plus cosine squared of theta all over the all over the sine squared of theta. Once again, sine squared plus cosine squared is equal to 1, and 1 over sine squared would be a cosecant, so negative 1 over sine squared is a negative cosecant squared of theta. So all of these, so with knowing this one and this one, you can derive the other 4. And you typically don't have to go all this way to figure out the derivative. At about this stage, I've done it enough times that I remember, oh, I would get a negative 1 over secant squared. So if it's hard, if you're like me and you don't like memorizing a lot of different things, try and memorize 2 big things, and from those 2 big things, you can build everything else you need. So let's get some more paper. We'll use those as we need. So let's do an example. This will be example 2. What we have is we've got some curve defined by y is equal to the secant of x divided by 1 plus the tangent of x. And what we want to do is we want to find where on this curve does this function have a horizontal tangent line. Where is slope of y equal to 0? Where does it have a horizontal tangent line? Where is the slope equal to 0? Where or what values of x make y prime equal to 0? Well, we need to calculate y prime. Y prime is going to be equal to, we're taking the derivative of a quotient, we'll apply a quotient rule. It says low, 1 plus the tangent of x, times the derivative of the top, d dx of the secant of x, minus the top, times the derivative with regards to x of the bottom, all divided by the denominator squared. So that's equal to 1 plus the tangent of x. The derivative of secant is secant times tangent. Minus the secant of x times the derivative of 1 is 0 plus the derivative of tangent is secant squared. All of that is still divided by 1 plus the tangent of x squared. Perfect. So at this step, I would want you guys, so where's a good spot to stop? If you were just asked to give a derivative, 1 plus the tangent of x times secant of x, tangent of x, minus secant cubed of x all over 1 plus the tangent of x quantity squared is a perfect spot to stop for the derivative. But what we want to do is we want to take this one step further and figure out where this thing equals 0. Now it's kind of tricky with the way it's written, but we're going to use the fact that the sine squared of x plus the cosine squared of x is equal to 1. So if we divide both sides of this equation by cosine squared of an x, we see that sine squared divided by cosine squared, or tangent squared of an x, plus cosine squared divided by cosine squared is 1, is equal to a secant squared of an x. Solving for tangent squared says that the tangent squared of an x is equal to a secant squared of an x minus 1. And so we're going to distribute a secant of x and a tangent of x across 1 plus tangent of x. And we're going to perform this substitution. So first, we'll multiply. That'll give us the secant of x times the tangent of x plus the secant of x times the tangent squared of x minus secant cubed, all divided by 1 plus tangent of x quantity squared. So now we're going to perform that substitution. This becomes secant of x times the tangent of x plus the secant of x times tangent squared of x is secant squared of x minus 1 minus a secant cubed of x, all divided by 1 plus a tangent of x squared. We're getting close to the end, or at least we're getting close to a good point to take a breath at. Secant of x tangent of x plus secant cubed of x minus secant of x minus secant cubed of x, all divided by 1 plus tangent of x squared, positive secant cubed, negative secant cubed. I got a secant here, I got a secant here. I'm going to factor it out. Secant of x, and what's left over? A tangent of an x, a minus, and a 1, all over a 1 plus a tangent of an x squared. Okay, so this thing gives us the slope of that thing for any specific value of x. We want to know where that thing's horizontal. That means we want to know where this thing equals 0. The secant of x never will equal 0. Secant of x, as a refresher, is 1 over the cosine of x. And the only way to make a fraction equal to 0 is if the numerator equals 0. Well, 1 never equals 0. So that means this thing equals 0 when the tangent of x is equal, the tangent of x minus 1 is equal to 0, or the tangent of x is equal to 1. The tangent of x, well, that's the same as sine divided by cosine, so that's whenever sine and cosine are equal to each other. That happens at pi fourths, or plus n pi, where n is an integer. So what this says is that starting at pi fourths, this thing has a horizontal tangent line every interval of pi. Makes sense. We've got stuff that repeats periodically, so we would expect horizontal tangent lines to repeat. Should have pointed here. Horizontal tangent lines. So, like I said, this was a good stopping point if you were just taking a derivative. We wanted to go one step further, so we manipulated the numerator, because that's an incredibly difficult form to work with, into something that was much easier to work with to get to our answer. But for the sake of taking a derivative, that was fine. We can keep on trucking. So example 3, we'll jump over to Desmos real quick, but I'll set it up. So an object at the end of a vertical spring is stretched 4 centimeters beyond the position of rest. So we've got a spring and we've got an object. What happens is we take that object and we move it down and this gap is 4 centimeters from where it was to where it is. And then we let go. And the first thing we want to do is we want to find velocity. And the second thing we want to do is find acceleration. So this is an example of simple harmonic motion. And what simple harmonic motion means is things are going to oscillate back and forth. The position of this block can actually be given by the function s. S of t is equal to 4 times the cosine of t. So that means its position at for any value of t can be given by this function. This box is effectively going to oscillate from 4 inches beneath to 4 inches above its position of rest. Simple harmonic motion ignores friction, it ignores air resistance. It's just a simple, pure form of motion. So the first thing we want to do is find the velocity of this box. Well, that's the derivative of its position with regards to t, which is equal to a negative 4 times the sine of a t. And its acceleration, well, that's the derivative of its velocity, of t, and that's equal to negative 4 times the cosine of t. And what we're going to do is we're going to graph all three of these in Desmos and make observations about their relationships.
Okay, so what we have here is we have the graph of S of t, V of t, and A of t. Or we've got the position, which you can really think of its displacement. We pulled that block down, but its displacement, we stretched it 4 centimeters was our unit. So even though it got pulled down 4 centimeters, that is still represented by a positive 4. So the second we let go of the object, and I'll go over here, it's going to start to move back. Now it's going to be moving up despite the fact the position makes it look like it's going down, but it's going from a positive 4 units away, and now it's going to go past where it used to sit, and then it's going to begin to overcorrect, if you will. It's going to be pulled back up a certain amount. And then gravity is going to have an effect, and it's going to pull the object back down, and it's going to oscillate. But take a look at what's going on. The second we let go, it doesn't have any velocity, but it has the strongest in magnitude acceleration it's going to have. When its velocity is 0, it's going to be accelerating as quickly as possible. As we return our position back to the middle, we're at equilibrium. We're still moving, but if we could pause time for a second, you can see our acceleration is actually going to go from negative to positive. What that means is we are getting faster, and now we're going to start to get slower. Our velocity is changing directions. We're going from moving in one direction to moving in another direction. And we continue. Now we get, keep going. Now we get to the point where we're going to start to return the other direction. So our velocity is going to our velocity is going to go from negative to positive. When our velocity goes from negative to positive, that usually indicates a change in direction. And that's what we're doing right here. As we return past equilibrium, our acceleration goes to 0, and then it starts to accelerate more quickly. So this is just the relationship between sine, cosine, well really it's the relationship between 4 cosine of t, negative 4 sine of t, and negative 4 cosine of t. I'll put this graph up on Blackboard for you guys as well.
Cool, so let's do another example. Well, this is example 4. What we have is we have some function f of x, and it's equal to the cosine of x. And what we're going to do is we're going to find the 27th derivative of f with regards to x. Blank. That's a joy of figuring out. So, there's going to be a pattern. Whenever the book asks you for the 27th derivative, the 34th derivative, something like that, they do not want you to actually do the derivative 27 times. Let's see what happens if we start off with f of x. That's equal to the cosine of x. Well, the derivative of cosine is equal to a negative sine of x. The derivative of a sine of x is a cosine of x, so we get a negative cosine of x. The derivative of cosine of x is a negative sine of x, and that negative and the other negative would cancel out, get us back to a sine of x. And now the fourth derivative is going to be back at a cosine of x. And it repeated. Well, the fifth derivative, well, it's going to double back. It's going to be a negative sine of x. The sixth derivative is going to be a negative cosine of x. The seventh derivative is going to be a positive sine of x. And the eighth derivative is going to be equal to a cosine of x. And we're going to repeat. Well, awesome. It seems like every group of four derivatives we get back to where we started. And that's true. So what we want to do is we want to figure out how many times 4 goes into 27. And we care about the remainder. Well, 4 times 6 is equal to 24. And when we subtract those, we get a 3. A remainder of 3. What this says is, so the fourth derivative is cosine of x. The eighth derivative of cosine the fourth derivative of cosine is cosine. The eighth derivative of cosine is cosine. The 12th derivative of cosine is cosine. The 16th derivative of cosine is cosine. The 20th derivative of cosine is cosine. The 24th derivative of cosine is cosine. So then we're back at the 25th, the 26th, the 27th, and we see that the 27th derivative of cosine of x has to be equal to the sine of x. Like I said, don't actually write out 27 derivatives. We're actually looking for the pattern. And if we wanted to, just another example from this, if we wanted to say figure out what the 42nd derivative, the 42nd derivative of cosine of x is, well, we would be able to do 40 of these groups. We know that the 40th derivative of cosine is going to be a cosine. And then 2 more would be a negative cosine of x. Because we did, how many times did 4 go into 42? That was 10. But the important thing was that our remainder was 2. If your remainder is 2, you'd be here. If your remainder was 1, you'd be there. A remainder of 0, you'd be there. And a remainder of 3. You shouldn't get a remainder of 4. A remainder of 4 is actually a remainder of 0. So it's going to repeat. So I've got 2 more examples for you. This is going to be example 5 and example 6. Both of them are going to use the fact that the limit as x goes to 0 of the sine of x divided by x is equal to 1. And we're going to come up with 2 clever ways of using this. So the first thing we want to do is we want to use this identity to solve the limit as x goes off to 0 of the sine of 7x divided by 4x. Well, we need these things on the inside to match. We have an x on top and we have an x on bottom. Well, we have a 7x on top and we could pull that 4 out if we wanted to, but what we don't have is we don't have a 7x in the bottom. We can put one there if we need. We're going to do that by multiplying top and bottom by 7/4. So I'm going to take this 7/4 and I'm going to move it out front. And this 4 is going to cancel out with that 4. And what we're left is with 7/4 times the limit as x goes off to 0 of the sine of 7x divided by 7x. So, this is effectively that, just written a little bit different. What it says is, as the denominator goes to 0 and the numerator go to 0, as the argument of sine goes to 0 at the same rate as the denominator goes to 0, then that limit is equal to 1. Well, we've got 7x on top, 7x on bottom, and x is going to 0. That's going to be equal to 7/4 times 1, or 7/4. Another way is if we wanted to take the limit as x goes off to 0 we'll do x times the cotangent of x. Well, whenever I see cotangents, tangents, secants, or cosecants, I always turn them into sines and cosines. Doesn't always help, but it can. Perfect. So, I'm sorry, that is the tangent, not the cotangent. There we go. So we have x times the cotangent of x. We have x times the cotangent of x. Now, multiplying by x is the same as dividing by 1 over x. So this is equal to the limit as x goes to 0 of the cosine of x, and we're going to divide by 1 over x. So we get a sine of x over x. Well, we know what the limit as x goes to 0 of sine of x divided by x is. That's equal to 1. And as cosine goes to 0, that's also equal to 1. So this limits to 1 over 1, or just a plain old 1. So, kind of looking for clever ways to use this limit. We could also use the one with cosine, that the limit as theta goes to 0 of the cosine of theta minus 1 over theta, that's equal to 0. You might find yourself using that in your homework too. But that wraps it up. Really, the big 6. I have them earlier in the video. It's the derivative of your 6 trigonometric functions. It's sine of x goes to cosine of x. Cosine of x goes to negative sine of x. Secant of x goes to secant of x. Tangent of x. Cosecant of x goes to negative cosecant of x. Cotangent of x. Tangent of x goes to secant squared of x, and cotangent of x goes to negative cosecant squared of x. Tangent squared, yeah, perfect. That's why they pay me the big bucks. And these are derivatives, and for good measure, these should be equal signs. Really, all of these 4 come from these 2. You get them using your quotient rule typically. I would challenge you, I would encourage you to try and derive all 4 of these from these 2. For personal enrichment is a good way of thinking about it. But not for personal enrichment, because I require you to do so. Go off and do 1 through 13 every other odd. Do 31 through 35 odd. Do 39 through 47 every other odd. Do 51 and do 53. This is your guys' homework. Alright, everyone have a nice day. I'll talk to you next time. Bye-bye.